Hello friends, today's lecture will be on fracture. So after we do, if you remember the tensile curve, okay, we start from elastic deformation, then we go into the plastic deformation range. In plastic deformation range you have a uniform deformation, okay, and then you have a necking and then non-uniform deformation, and at some point you will have fracture in the material. Okay, so we want to understand this phenomena of fracture, that what does it mean, and does it depend on the different materials. In different materials do we have different type of fracture mechanism. Okay, so all those things we will like to see. This is one of the some very famous photographs to bring out the importance of understanding of fracture, and actually importance of materials also. These are some ships which were made in World War II. These were called Liberty ships, and most of this ship failed like this. You can see the fracture, the ship has fractured into two parts, okay, completely two parts it has fractured, and a big ship like this just fractured into two parts is a kind of a very difficult thing to understand. Okay, so people found out that there were problems in the material, there were problem in the fabrication and so on. Okay, and a lot of improvements took place after that. In fact, Titanic also, if you see, it was a kind of a fracture problem only, that the material was not of good quality. A lot of carbon used to be there in the steel at that time. Okay, and when the iceberg hit the Titanic ship, okay, so it fractured. Instead of having a ductile fracture or ductile deformation, it actually fractured in a brittle manner. Okay, and then once the crack started, it under the massive load of that ship, that propagated, and the whole ship got again, I think, divided into two parts. Okay. So types of fracture, if you want to see, there can be two type in which we can divide. One is brittle. Okay, so brittle is a very difficult and problematic kind of fracture, because you don't get any warning. So once it starts, and then it will go at a very fast rate. So you can say it is a fast fracture also. So brittle fracture, in this you do not have any plastic deformation or very small plastic deformation, and that is why there is no warning. Okay, so you will not know when you have reached the fracture stress of the material, whereas when you have plastic deformation, it will take a lot of time in getting deformed and then go into the fracture mode. Okay. And before that you will actually be able to see that something is deforming out of shape. The separation in this case is normal to tensile stress, because it is kind of a decohesion between the two atoms. So all the atoms bonds kind of break. Okay, and usually observed in BCC and HCB material. FCC, because it is very ductile, the FCC structure materials are ductile, you do not see there. In BCC also you will see only at very low temperatures. At normal room temperature you may not see it. Okay, so there is a effect of temperature also here. Okay, in HCP of course you will see this kind of fracture, brittle fracture. And ductile fracture, you will have appreciable plastic deformation which occurs prior to or during the fracture process. In a tensile test, pronounced necking before fracture, cup and cone fracture. So when we do tensile test also, we will clearly be able to tell you that which one is a ductile material, which is a brittle material, depending upon how they are getting fractured. So if you do a tensile test of brittle material, just taking the gauge section, actually your material will divide into two parts. Okay, and the fracture has taken place normal to the tensile stress, whereas in case of ductile material, the material will actually neck first. Okay, and in this also there is a kind of a very nice geometry to that. Okay, so in one case it will be a cup, and in the other part it will be a cone. Okay, so it separates like this. So, it is called a cup and cone fracture. Fracture mode depends on different parameters. So, you can have as a function of material, so crystal structure or alloying. Okay, already we have seen that different crystal structure behave differently. Temperature, as I told you that temperature plays very important. So, in BCC material, as a function of temperature, it will either show as a brittle fracture as a brittle material or fracture as a ductile material. Okay, so, temperature plays very important role here. State of stress, whether it is a plane stress condition or plane strain condition, rate of loading, strain rate. Okay. So, if it is high strain rate, then sometime material fracture as a brittle material. If you are doing the same test on the same material, but at a slower strain rate, it will fracture in a ductile manner. Environment, so basically corrosion and if hydrogen is there, hydrogen embrittlement is there. So, depending upon the environment, the fracture will change. In some cases, a ductile material will fracture like a brittle material because it has already corroded. Okay. So, all these factors will determine the fracture mode. So, if you kind of want to see the whole kind of a overall scene or overall difference between different fracture modes. Okay. So, you have brittle here and ductile here. Okay. So, this is brittle here and ductile here. Okay. And this is at a high temperature, this is at low temperatures. Okay. So, at low temperatures in brittle material you will have a fracture like this, where the crack is going through the grain. Okay. It is a cleavage fracture we say, or you can have intergranular brittle fracture. So, you can see in this case the crack has gone through the grain boundary. So, it is called intergranular, and this will be called as intragranular. Then you can have plastic growth of voids. So, you can see some voids are forming within the grain here. Okay. So, within the grain it will be transgranular or intragranular, and between two grains it will be intergranular. Okay. So, void can be at the grain boundary or voids can be within the grain, and these voids will then grow, then they will connect with each other and the material will fracture. And this is for ductile material, rupture by necking or shearing off. So, you can see that necking is taking place, and at the end you will have a fracture here as a point fracture or cup and cone fracture, or you can have shearing in form of shearing. At high temperature again you will have formation of voids at the grain boundaries. Okay. So, it is intergranular fracture through formation of voids, or there can be formation of wedge at the grain boundaries, then it is called wedge cracks. Growth of voids by power law creep, another, when we will see creep you will see again this type of fracture taking place. Okay, or it will be through necking, as we saw at the low temperature also. Okay. Now, coming to the brittle fracture, okay, it is easier to understand the brittle fracture first. Okay. So, we will first look at the brittle fracture. Okay. So, before coming to that, let us see what will be the theoretical cohesive strength. So, basically what is we are saying is, when we have fracture, so suppose this was the material initially, of course you had atoms here, okay, and there was atomic bond between them. Okay. So, when I am saying that it is fracturing into two parts, okay, so it is fractured here. Okay. So, basically I am breaking these bonds between the atoms, and then it will be the material will be in two parts. So, I can kind of get an estimate that what kind of stress is required to do this breaking of all the bonds. Okay. So, if I take a material of this size, let us say, there will be like millions of atoms and millions of bonds that I have to break to take into two parts. Okay. So, suppose the atoms are there, then there are bonds between them, this is a fracture plane, and I am simultaneously rupturing all the atomic bonds for fracture to take place. So, if I want to do that, the theoretical calculation, the derivation I am not giving here, you can look in the book, for example, by on mechanical metallurgy by Dieter. So, sigma theoretical will be equal to E by 2 pi. It is similar to what we saw earlier in case of shearing also, that when I want to shear all the atoms at one go, okay, I have to break all the bonds, okay, create new bonds, and by that I will slip it by one atomic distance, okay, and what was the stress required to do that. Similarly, here now in this case I am breaking all the bonds between the atoms simultaneously, and this is the strength or stress required to do that, that is equal to Young's modulus E divided by 2 pi. Young's modulus already we know for most of the metallic material, it is in the range of gigapascal. But the engineering material, when we try to find out the fracture stresses, these are around 10 to 1000 times lower than the theoretical value. Okay. Already we have seen that it is usually in megapascal or something. So, maybe 2 or 3 order of magnitude difference between what we get from theory and what we see in the experiments. Okay, so again in this case also there must be something in the material, okay, which is bringing down the this strength of the material. Okay, so in case of plastic deformation or shearing, we said that the defect is dislocation, that defect is dislocation which is bringing down the theoretical shear strength of the material. Okay. In this case also we are going to have some defects, and these defects are called cracks. Okay. So, the reason for bringing down this theoretical strength is that there are fine cracks present. Okay. So, first time it was proposed by Griffith. Okay. So, and he proposed that for brittle materials, because fracture process is very easy to understand in brittle materials, because there is no plastic deformation. So, only the separation between the two material is through breaking of the bonds, okay, without any plastic deformation. So, Griffith offered an explanation for the discrepancy between observed and theoretical cohesive strength. Of course, what he offered was only applicable for brittle material like glass, okay, not even brittle metals, it is brittle material like glass. And Griffith proposed that brittle material contain large number of fine cracks. Okay. So, what happens when you have large number of fine cracks? For example, one crack is shown here in this figure. Okay. You are applying force F. Okay. So, the stress on the system will be given by sigma, with let us say we call it as nominal stress, okay, that is force upon, this is the area of cross sectional area of the sample. Okay. So, the nominal stress is only force upon per unit area. Okay. Now, when you look, if you have a crack in the material, what will happen is that locally the stress will be very high where the crack tip is there. Okay, and this is called stress concentration. So, wherever you have a sharp some discontinuity like this, you are going to have a very high, for the nominal stress which you are applying, the locally the stress will be very high. Okay, and that is why, if you remember, when I was discussing the tensile test also, I said that when we prepare the sample, tensile sample, we do not prepare it like this. Okay. The reason is this sharp corner will impose or we will give rise to stress concentration, and the locally the stress here will be very high. So, this kind of sharp corner like this will act like a crack here. Okay. So, instead of that, what we do is we give a kind of a curvature like this, okay, and to minimize the stress concentration. Okay. So, what will happen is that where the crack tip is there, the stress is very high. So, this is my sigma max, okay, and as you go away from the crack tip, the stress is equal to whatever you will get from the force per unit area, and the dimension of the crack is also defined here. So, the total dimension is 2c. Okay, we will, if it is an inside crack, we will take only the half of that, that is c. If it is a surface crack, suppose it can be here, then we will just take the whatever is the total length of the crack, which is going to be c. Okay. So, if it is inside crack, then the whatever crack length is there, half of that. So, we will always say that it is 2c. So, half of that will be c. If it is surface crack, then we will just take the c here. Okay. So, sigma max will be equal to, you can have an expression also here, it will be equal to 2 sigma nominal into under root of c by rho. Okay, I think that. So, when you have fine crack, it produces a stress concentration, okay, and its magnitude is closer to cohesive strength in localized region. So, what will happen that the overall stress is very small, okay, and we are seeing that, okay, the material has fractured at this stress. The locally the stress will be very high, that can be close to the cohesive strength of the material. So, locally here it will reach the what we have calculated for the given material. So, sigma max can reach E by 2 pi locally. Okay, whereas what you are measuring, it is only sigma nominal, that is why you feel that, okay, it is fracturing at very low stress. Okay. So, as you can see, this sigma max depend upon the crack length. So, if you have a larger crack length, then the stress will be also be higher, the stress concentration at that crack length will be higher. Okay. So, it will be easier for you to fracture the material. If the crack is sharp, the radius of curvature is small. Okay. So, for a blunt crack, the radius of curvature will be more. Okay. For a sharp crack, the radius of curvature will be small. Okay. So, because it is coming in the denominator. Okay. So, let us call this a rho 1, this rho 2. So, rho 1 is greater than rho 2. So, when my rho is or crack is getting sharper and sharper, this value will be smaller and smaller. So, my because it is in the denominator, the sigma max value will be even higher. Okay. So, bigger crack and sharper crack, okay, make the sigma max even higher. Okay. You will have a higher local stress, and it will be easier to fracture the material. Okay. So, overall stress is much lower than the local stress. Okay. So, this is what you have as we discussed in the. So, Griffith criteria propose that or states that a crack will propagate when the decrease in elastic strain energy is at least equal to the energy required to create the new crack surfaces. Okay. So, what will happen when you have, suppose, material, there are atoms here, and you are applying a stress on the system. Okay. So, all the bonds are under stretched condition. So, there is a elastic strain energy. If you are not applying any stress, the atoms are at their equilibrium condition at minimum potential energy. So, when I am applying any stress on the system, okay, all these bonds are now stretched. So, they will have some elastic strain energy. So, they will have some potential energy associated with them. Okay. So, when you create a crack, so basically you are breaking the bonds here. So, you are releasing this elastic energy, my atoms are again going into the relaxed state, okay, and these bonds are now broken. So, there is not going to be any elastic energy, but the problem is that when I fracture the material, I am creating two new surfaces. So, there will be some surface energy associated with this which is called gamma. Okay. So, my strain energy is released, but I am creating two new surfaces. So, that is what he proposed, that a crack will propagate when the decrease in elastic energy, whatever is the decrease in elastic energy due to the breaking of bond, is at least equal to the energy required to create the new crack surfaces. When it is equal to the energy, surface energy of the two new surfaces. So, suppose a crack of length 2c is present inside the plate or c at the edge, okay, and we are taking the thickness of plate is negligible. So, it is a plane stress condition. Okay. So, for that the decrease in elastic energy per unit of plate thickness due to formation of crack is given by a relationship like this, UE pi c square sigma square by E, and surface energy increase due to presence of crack will give you new, because of two new surfaces, this is surface energy now, it will be equal to 4 c into gamma s. Okay. And the total change in potential energy due to formation of crack will be delta U, the change in potential energy. So, US plus UE. So, according to the Griffith criteria, the crack will propagate under a constant applied stress if an incremental increase in crack length produces no change in total energy of the system. So, when I am increasing the crack length, okay, if there is no net change in the energy of the system, the crack will be a stable crack and it will propagate. Okay. If surface energy is high, then it will not propagate, because creation of surface energy makes the total energy of the system will increase. Okay. If the elastic energy is high than the surface energy, then obviously the crack will be a stable crack. So, the minimum criterion for stable crack is that at least they are, both these two energies are equal, or there is no net addition of energy during this process of crack propagation. Okay. If the energy is negative, it is even better. Okay. But at least it should be, there should not be any net addition to the energy to the system. Okay. So, basically the change in energy delta U as a function of increase in the crack length, that should be 0. Okay. So, d by dc of this particular equation. So, US you are adding the energy, U is you are taking out the energy, okay, by breaking the bonds. So, that is why the negative sign is here, and what will be the change in that as a function of change in the crack length. Okay. So, a simple differentiation you have to do. So, it will d by dc of 4 and gamma s will be constant. So, it will be dc by dc. So, it will be 4 gamma s minus all these things will remain constant. So, this is c square. So, it will become 2 c. Okay. So, 2 pi c gamma sigma square by E, okay, equal to 0, and that will give you the required stress for fracture. It will be 2 E gamma s upon pi c to the power half. Okay. So, this is the stress required to propagate a crack in brittle material as a function of the size of the micro crack. Okay. So, if the crack is bigger, you will have small fracture stress, the fracture will take place at a small stress. Okay. For a thick plate plane strain condition, okay, the equation will be something like this, slight change from the previous condition. So, 2 E gamma s by pi c. So, 2 E gamma s by 1 minus nu pi c. So, there is a additional contribution of Poisson's ratio here, because we are considering a thick plate. Okay. So, thickness is more in this direction. Okay. So, it is a plane strain condition, and for that we will consider the Poisson's ratio also here. So, Griffith equation shows a strong dependence of fracture strength on crack length. Okay. It is said it is able to predict satisfactorily fracture strength of perfect brittle material, however fails to predict in case of metal, even brittle metals. The reason metal that fail in a completely brittle fashion undergo some plastic deformation prior to fracture. Okay. So, these equations are valid only for perfectly brittle material, in the sense if you see a stress strain curve of a perfectly brittle material. So, it is, this is stress, this is strain. So, for a perfectly brittle material, it will fracture without any plastic deformation. So, it will take place in the elastic range only. Okay. That is why you see we are using Poisson's ratio here. Okay. So, this whole analysis of Griffith criterion or Griffith theory is for the elastic range only, or elastic deformation only. So, there is not going to be any plastic deformation, whereas in metals, okay, for any metal, though it may be a brittle metal, if you see the stress strain curve, okay, it will be something like this. Plastic part, small elastic part, some plastic deformation will always take place locally and then it will fracture. So, this deformation plastically kind of modifies this whole analysis, okay, and that is why it is not able to predict very well in case of metals, brittle metals. Okay. The reason is this, as you can see that we said that where the crack tip is, you will have stresses very high. Okay. So, your sigma max is going like this. So, this is the elastic stress distribution just we saw, this is my crack tip, okay, and because of that this is my stress, increase in stress next to the crack tip. But in my metals where there is some plastic deformation, what will happen as soon, if suppose this is my yield stress of the material, okay, then what will happen as soon as this locally the stress go beyond that, instead of straining the bonds, what will happen is there will be shearing of bonds, okay, basically shearing of the planes. So, material will shear. So, instead of the stress going beyond that, what will happen is locally the material will deform, okay, and instead of this stress distribution, you will have a stress distribution like this. It will not go beyond the yield stress. So, elastic distribution after local yielding will be like this, okay, and you can understand that by modifying the crack tip. So, instead of a crack tip like this, the overall notional crack tip can be something like this. So, actually what we have done is we have increased the, this is this was the radius of curvature. Now, the radius of curvature has increased, it has blunted the crack tip. So, instead of very sharp crack tip, now you have a more blunt crack tip. Okay. So, and if you remember the expression which we use, the rho comes in the denominator. So, if your radius of curvature is increasing, then the maximum stress in front of stress also will come down. Okay. So, plastic deformation at the root of the crack result in blunting or increase in the radius of the crack tip, and that increases the fracture strength of the material. So, now it will fracture at a higher stress. So, thank you. With this we have covered the basically the fracture introduction, and we have seen the Griffith criterion. Okay. So, in the next class we will conclude the fracture lecture, and we will see that how you can do the analysis in case of slightly brittle metal for the cracks, and we will also see that how the different fracture will look like, the ductile and brittle fracture when we look at it into the microscope. Okay. So, thank you.